Questions? Anything you'd like to ask? Now, one of the things that is pending is the name of somebody who's willing to act as class representative. So please, one of you, or once some more people show up, if you do, one people be class representative. Sorry? Of course. Yeah. Because essentially what it means is, other than liaising with me, there is a department committee or group of representatives who have meetings. So presumably you can attend, and you essentially you say, increasing returns to stealers as the economy goes. It's fine. Okay, so quick recap, right? We've been doing I'd say quite a few things conceptually. So apart from what we started with, essentially an example economy to motivate things, what we did was we set up what we call an abstract economy. So the idea was, you say, well, you have a bunch of commodities, L, and then you have agents who are described by their consumption sets, by their endowments and their preferences, and in order to specify how they interact, we say that for each of these commodities, you have a market, and on that market, a price is quoted per unit of the commodity. Now, given this vector of prices for all the commodities, the agent's budget set is defined, and each agent chooses the best point in that budget set at those prices. And agents behave as though they cannot influence prices. That's competitive to some extent. A competitive equilibrium is a situation in which, at the given prices, all agents are not only choosing their best points in those budget sets that are induced, but the allocation is feasible in that market's clear, is another way of putting it. Okay, so that was the notion of competitive equilibrium in an abstract economy. And then we said that a really nice property of this equilibrium is that under the assumption of local nunciation, which is really very mild, every competitive equilibrium allocation is Pareto. Okay, and that in some sense was our objective, to specify when do you get that result. And that's when you get the result. Okay, so that was in what we call an abstract economy. And then we went ahead and we said, now look, can we think of the world that we live in can be described as an example of an abstract economy? That was the next approach. We said, all right, so what are the things that we are missing in terms of the model of an abstract economy? Well, we didn't have any notion of time. In the world, of course, things happen not only today, but over time. And we don't really know a lot about the world. Over time, we learn. Okay? So we said, we'll start with something called a date event tree, which describes the way the world evolves. All agents take that as given. You might be interested in only one part of that date event tree. But that date event tree is given to you, and you cannot influence the way in which nature makes her choices. The date event tree specifies time. It could be just one period. It could be many periods. And it also specifies how uncertainty evolves over time. And at the end of it, you have a set of mutually distinct outcomes. So one and only one of them, mutually exclusive outcomes, one and only one of them will define the state of the world, is the way it's formally described. And then again, at each of the date events in that date event tree, you will have a bunch of physical commodities. All these commodities taken together define your space of commodities, and then you apply the machinery that we learned about earlier to that much more special economy in many ways. It's actually a very general economy. And there you ask, well, again, you want a market for each date and state contingent commodity. That's important. So it's a price for a date and state contingent commodity. These prices are paid at an initial market for all of these commodities. Payment in terms of delivery of the commodity. So these are contracts that are signed, and delivery is made if and only if that particular date and state contingent situation actually occurs. So if nature chooses that particular outcome, that's when payments are made, deliveries are made or received. Otherwise, there are no deliveries to be made. So in any other state contingent situation, you will not get any delivery of a contract that specifies delivery somewhere else, but payments are made right at the beginning. This is the whole point. Okay? In that framework, again, with this competitive structure of markets, you have a single budget constraint. It's quite a complicated problem, but actually it's very nice if you think about it. And in that framework, when agents maximize given those prices and those maximizing demands, if they are compatible in the sense that the allocation is feasible and market's clear, then again you have a competitive equilibrium, which is a special name. It's called the Arrow-Debreu competitive equilibrium. Right? Once again, under local non-cessation, which in itself is a mild requirement, you have Pareto optimality. So that's the sort of world in which, in fact, there is nothing more to be said. Things are working beautifully, markets work, and it's really nice. That's what we had seen. And then at the end, I said, look, there is a particular case which we call a canonical model. And in that canonical model, which is where we stop, yes, I'm not writing this board, as I've said before, I'm not used to writing on these anymore, so it takes me longer to write. But let me just put down what a canonical model is. So at date, there are only two dates. Just three dots. At the first date, t equals 0, there is only one state of nature. And at the second date, t equals 1, there are s states of nature. So your commodity space will be, and you have L physically distinguishable commodities at each date. So your commodity space is R L times 1 plus S. So I'm not writing what they are, but I'm writing what the notation is. Okay? And you will have agents. Each agent's consumption vector will consist of components xi0 and xi1 all the way through xi capital S, and each of these sits in RL plus. Okay. So in each at time period 0 and in each state in time period 1, you have a vector which sits in RL plus. You have an endowment which similarly is omega I, it will be omega I0, omega I1, omega IS. Okay, and you will have references. I'm not writing out separately. Now there is nothing here. When we moved to Arrow-Debreu, at the beginning I did say that when you have an economy with two states of nature, a particular case, it might have sounded as though I was saying that's always the case, but it's a particular case of a utility function there is expected utility. But expected utility is a particular case. It's a case in which it's actually easier to work through things, because expected utility representations are possible under relatively strong assumptions. Okay? But in general, your preferences will be over bundles. And your preferences will reflect your beliefs about the probability with which various outcomes occur. Okay, so it's very natural for you to all of a sudden have a question about this on your own. It's very natural. And the more you think about it, the more you will realize how nice the structure is. Completely unrealistic, but actually very nice in terms of what it captures. What is unrealistic is the structure of markets. The description of the economy is actually very nice. Okay, and the description of the economy, if I'm not mistaken, it's formalized by Hicks, the 30s. And the economists have been thinking about these things for many years. The formulation of Arrow-Debreu is from the 50s. Okay? Now, what we wish to do is, and in an Arrow-Debreu economy, one can also talk about prices, but since I'm going to talk about some other kinds of structures now, I'm not going to bring in the notation here. You will see this notation on a problem set where you're asked to think about a result that we will talk about today, which is Arrow's equivalence result. So now what we want to talk about or sequence economies. So what we're going to say that, look, it's all very nice to talk about arrow the bro and contingent commodity markets, etc., but there are relatively few of these. Right. So what we actually see are two special kinds of markets. One would be spot markets, which is to say, given that you are either at date 0 or at one of these states at date 1, you have L markets in which you can trade in that time and state contingent situation. Okay, so these are in some sense the regular markets in which all of us buy goods and sometimes we sell goods. Most of us don't sell anything other than when we started selling labor. Okay? But if you wish to, you might be selling something on eBay. Right? So these are spot markets. So you will have L of these markets at each node in that tree. Okay, so L at 1 plus S nodes. So at each of them, you will have a spot market, and we'll denote the prices by P0, P1, PS. And we will have asset markets. Asset markets, in general, would be a catch-all. They could reflect all sorts of things. Okay? So they would reflect borrowing from a bank, bank deposits, loans, stocks, bonds. All of these would be examples of asset markets. Clearly, that's not the direction in which we are headed. We need to be a bit more specific about what we need. Okay, so for us, an asset market allows is what it actually does, and what an asset does, and this is true in general. An asset will allow you to transfer income either across time and or across states of nature. This is the idea. Okay? So we'll come to examples in a moment. So an asset for us is an object which is characterized by its payoff. This is the key point. Okay? So payoffs are specified, which in our case, since we're looking at something which is a bit more special, it suffices for what we wish to do. In our case, an asset will always pay off in the first commodity. So an asset specifies quantities are, okay? So for the jth asset, Rj is specified by a vector Rj1 to Rj capital S. These are quantities of the first physical good. So let's say the first physical good is bread. So this vector specifies quantities of bread, positive or negative. You might be making a promise to pay or a promise to receive different quantities of bread in the different states. Many of these numbers could be 0. There's no problem with that. Is it okay? So an asset specifies quantities of the first good that are to be paid or received in the different states of nature.
What do you mean by first good?
As I said, you have L goods.
Yeah.
So we've specified our economy now. It's a canonical economy. Okay? So you have L goods in each state, and physically they're the same good.
Yeah.
Okay? So it's bread that you will buy tomorrow.
Oh, okay.
Bread that you buy tomorrow or sell tomorrow, actually consume tomorrow, if it's sunny. Bread if it's snowing. Bread tomorrow if it's raining. Bread tomorrow if, God forbid, there is an earthquake somewhere. Each of these are different states. But the first good, we specified it to be bread. Assets can be described much more generally.
Yeah.
It becomes more messy to handle the notation. For what we wish to do, this is sufficient. And I'll give you some examples in a moment. Is that okay?
So those are the quantities that...
Sorry?
So
To understand again, these are the quantities at different individual points. Like if you want bread, get bread at RJ1. That's a different quantity compared to RJ2.
So the asset is specified exogenously. Okay?
Yeah.
So the jth asset is specified by a vector of quantities, many of which could be zero. And these are quantities of bread in the different states of nature.
Yeah.
How much you're able to consume, that I will specify a bit later. Because you can buy different assets in different quantities. What you get to see in your budget constraint at state S will depend upon the combinations of different assets that you want. You're not restricted to buy just one unit of just one asset. You have to respect the budget constraint, but beyond that, it's quite general. And of course, there will be a price, which will be determined in the market, which we will denote by Qj. Is that okay? Making sense? So one possibility is if we wish to replicate our Arrow-Debreu date and state contingent markets. Okay? So there, bread in the second state of nature will be replicated by an asset that pays 1 unit of bread in the second state of nature and 0 everywhere else. So you can replicate Arrow-Debreu contingent markets, but you will need many assets to do that. Because you will need one, and you could do it only with bread, because we're assuming that all your assets pay just in the first commodity. If you were to allow assets to pay in all commodities, you could do that. But you'll have a huge number of assets, which reflects the fact that Arrow-Debreu has a huge number of markets. Okay? So this is a more realistic and a more parsimonious description. Try to say it's nicer. And that's why we're concerned as to what we get with this. Okay? Another example of an asset is a so-called futures contract. Okay? A futures contract, so there are different kinds of contracts. Some are called forward contracts. What I've described so far can be thought of as I know the state contingent commodities are actually examples of so-called forward contracts because they pay in certain contingencies. Forward contracts aren't that specific, but still, contracts for oil, etc., are typically forward contracts. A futures contract, on the other hand, typically is definitions for these things sometimes change depending on what you're reading. But the standard notion of a futures contract is an asset that pays regardless of what nature does. Okay? So an asset which always pays 1 unit of bread, regardless of the state of nature, is an example of a futures contract. And there are, of course, many, many other examples. Now, what we want to talk about is a notion of equilibrium for such an economy. And the name for that is an Arrow-Radnor equilibrium. Okay. Many of us are of the view that Radnor should have received the Nobel Prize. Both Arrow and Debreu did receive the Nobel Prizes, but unfortunately Radnor passed away last year without having received the Nobel Prize. Okay. But it's Arrow-Radnor, and as Radnor used to like to say, he's not an economist, he's a statistician, because he got his doctorate at Chicago with Jimmy Savage, a very well-known statistician. So what are agents going to do here? Okay, so we've specified our markets, we've specified our prices. We still need to specify how do these things interact so that agents are actually able to take decisions. So at t equals 0, agents will buy a portfolio. So portfolio is a specification of different quantities of the different assets. Okay? Theta I in, we have J assets. Capital J assets. A portfolio is a quantity of each of the assets. Okay? So they buy the assets using their endowments and trading in those endowments in spot markets at date 0, and then at date 1, depending upon the state of nature that gets realized, you get a payoff. And that payoff will allow you to buy more or less than your endowment in that state of nature would have otherwise allowed you to buy. Okay, so assets pay off at date 1, so I'm not writing all of that, you have them in your notes. And agents will continue to be price takers, and they will be rational, so they will choose the best point in their budget set. And of course, any contracts that you make must be honored. You can't really make bankruptcy for these situations. Why? Because we've ruled out asymmetric information. Can you incorporate asymmetric information? The answer is yes. It will of course give you much more restricted trading. We don't want to get into that for a moment. You'll see what our purpose is in just a moment. So the budget set of agent I in these sequence of markets depends of course on prices at P0, P1, PS, and asset prices Q. And the budget set is quite simple to define, hopefully. So it's the set of consumption vectors, I'm going to write it out, R plus L1 plus S. If anything in the notation is not clear, because we're covering quite a bit of ground, please ask. And the portfolio in RJ such that, so I'm going to write out the budget constraint in a specific form, but before I do that, I'm going to write it down top here. So the usual way of writing our budget constraint would be P0 X I0, right? So that's the value of what this agent consumes at date 0, plus whatever the agent spends on buying or selling assets. So that's a vector in RJ, that's a vector in RJ, so the dot product, which we've defined earlier, gives you the total value of assets purchased or sold, positive or negative. That's important. Is less than or equal to P0 omega I0. Do we agree? That's a reasonable budget constraint at date 0? Right? Now, instead of writing that, I'm going to write it in the following form, because it's just standard in this literature. I'm going to write it as a net trade, as it's called. Is it okay? We agree that they're the same thing? Yeah, so that's the way I'm going to write it. So that's what I'm going to put here. P0 xi0 minus omega I0 plus q dot theta I less than or equal to 0. And then in each state of nature, I'm going to have payoffs. So again, this part I'm going to write in exactly the same way as I have already. So Ps dot xis minus omega is. And then on the right hand side, since I'm getting payoffs, I need to sum my payoff over all the assets, which go from 1 to capital J, and I need to see how much I'm getting from each asset. Okay, there is also a price here, which I'll write in just a moment. So it's the jth asset that I'm getting. So in order to keep the notation, so the way you have it in your handout, etc., at this stage, yeah. So at this stage, I haven't used the notation for the agent, so I'm going to remove it here. Okay, so I'll leave it for the endowment, but not for the choices. So this is just to make the notation a bit easier. That's all. That's not clear, please ask. RJS. So in state S, which is the one that we're looking at, so there are S of these different constraints. So S here goes from 1 to capital S. So in each state, I'll have a different constraint. So what is my payoff in that state? Well, it's the number of units of the jth asset that I bought times how much that jth asset pays me in state S. Yep.
In the notes, it says that the summation to the J is multiplied by
Yes.
price at the
Yes.
best point.
Yes. Yeah. So I said that earlier, that I'm going to tell you why. Remember, each asset pays in bread. Okay, that's our assumption. The first commodity being bread. So in order to make these compatible, I do need to make sure that what I have on the right hand side gets multiplied by the price of bread, which is PS and 1. So I think it's P1S is the way I have it. PS1 is the way I have it. That's why. It's also the case that in this sort of a framework, very often, you can actually assume that the price of bread in every state of nature is always 1. Okay, but we don't need to do that. Is it all right? So that's my budget constraint. So we have 1 plus S budget constraints now instead of the single budget constraint. It's already different. Is that okay? Given that we have specified a budget constraint, we can specify behavior. You will choose the best point in your budget state. That's all right. What's an equilibrium? It's a specification of all prices and actions such that all markets clear. Your markets are exactly the same structure as you had in Arrow-the-Brugh. You have L times 1 plus S markets for physical commodities. So each of them has to clear in the same way as in Arrow-the-Brugh. In addition, you have J asset markets. You have more markets in terms of market clearing. In Arrow-the-Brugh, in this economy, with Arrow-the-Brugh, you would have R, L, 1 plus S as your commodity space. So for each of these, you would get a price. So you get L times 1 plus S prices. Those are your spot market prices anyway. You have all those. In addition, you have asset markets. Okay? So I'm not writing out the details here. Questions so far? It's a lot to digest. You should be thinking about this. Again, I repeat, you will not be asked to write an essay on the Arrow-the-Brugh economy. Don't worry about that. I want you to try and force yourself to get your head around, in some form or the other, understanding what we are doing. And it will become clearer as we move along the course. Over the next 2 lectures, essentially, you will see how all this will fit in. I could have actually started with what I will be developing from tomorrow or the day after. Okay? And just told you, believe me. I don't think that's a nice way of doing things. And you're perfectly capable of understanding these things, at least trying to. Is that okay? Now notice a very important feature here. In Arrow-the-Brugh, remember, in Arrow-the-Brugh, the way to think about things is, before anything happens, prices get announced. So when you make your decisions, you actually see all those prices in the markets. It's completely unrealistic. That's a separate matter. But the assumption is you can see all those prices. Right? Over here, you're making your decisions about what assets to buy, what your theta is, at date 0. But the payoffs are available at date 1. At date 1, what you will be able to do with that additional income or any payments that you make will of course depend on those prices. But those prices are available at date 1, not at date 0. You need expectations. Now you see how sort of consistently nice Arrow-the-Brugh is, completely unrealistic. But at the same time, it allows you to bypass all these problematic issues. In Arrow-the-Brugh, you don't need any expectations. Because you're assuming that these are markets for trade and contracts. And all markets clear at the beginning of time. The auctioneer announces prices for everything that is relevant in the economy. Right at the beginning. Everything has to be done at one shot. Otherwise, you don't progress. That's not the case here. So what do? Well, we make a heroic assumption. We say that agents correctly predict prices. It's called perfect conditional foresight. So for any state of nature, each agent, although they might have different beliefs about the state of nature occurring, they will have identical price forecasts. macroeconomists have taken this another 30 yards and called it rational expectations. Now you see why it's such a problem. You realize this is what you need. Otherwise, everything that we do as economists goes into the garbage. You just don't know what to do, right? You can make all sorts of assumptions about incorrect expectations, and you can produce whatever you want. That's not a very useful way of doing anything. If you want to be able to say something sensible, you just have to make these assumptions. But it's important to know what assumptions you're making, so that at least you know with what confidence you can actually say that what you're doing is correct, or making any sense. Is that okay? Questions? So what do we want to do now? Okay, some of you have probably looked at the notes. What we want to know is when is it that this more realistic description of an economy gives you the same thing as others. We like what we get in Adelaide, but we know it's completely unrealistic. So when is it that what you get here is what you will get in Adelaide? And the answer is, so I've not defined the equilibrium on the board, but you have it in the notes. This is arrow 1953, about which there is a nice story that Arrow tells, or used to tell. Much of this work goes back many decades. Radner's work is from 1967, and this particular work is actually from 1972. Radner's 67 work was an asymmetric information. So Arrow tells a story that this paper was originally published in French. And it was translated and published in English in the mid-60s, early 60s. Okay. So he tells, someone asked him, one of the students I think asked him, what he thought of the translation. And he said, oh, well, this is like when someone was asked to translate. At that stage, it's probably too early for computers. Computers were doing mean counting by then. About translating the phrase, the spirit was strong, but the flesh was weak. And the translation came out, what was the translation? The alcohol was good, but the meat was bad. So, so anyway, what did Arrow show? So Arrow fundamentally showed the following. He showed that when you look at an equilibrium of an economy, so your economy is specified by characteristics. So that's given to you. And now you compare what happens when that economy permits agents to trade in Arrow markets versus trading in Arrow-Radnor markets. And you compare the two equilibria. Arrow showed fundamental, and this result is, a lot of finance is actually built around this result. So Arrow showed that if you have as many assets as states of the nation, and those assets they satisfy a technical condition called independence. The assets are not essentially duplicates of each other. Then the equilibrium outcomes in the two situations are identical. So if you want Pareto optimality in an Arrow-Radnor economy, you will need S assets, S independent assets. Okay, so that's Arrow's equivalence theorem. And before I write that on the board, let me just point out what it's actually saying in an example. So let me go back to our Edgeworth box example. Apples in state alpha, write it as alpha, and apples in state beta. And we said that if that's the endowment, then if you have markets for each of these two state contingent commodities, apples in each of those states, then you would be able to achieve a Pareto optimal allocation, like so. We agree? That was one of our motivating examples for Arrow. Now think of that as asset markets. Suppose you do have a spot market in each of the states. Since it's just one commodity, that's not going to do very much. So that you have that. But you do not have an asset market. You do not have a means of transferring income from state alpha to state beta. You can't get any choice. You end up at the endowment. This trivial example tells you, or you can think about borrowing and lending if you wish. If you don't have a bond, you will not be able to transfer resources across time. So there has to be a connection with how many markets you need. What Arrow did was specify what you precisely need. And it's got nothing to do with the structure that we've put together. You can replicate Arrow's theorem in the much more general case of a general data entry. That can be done. Okay, and that's where it gets taken over by finance and lots of notation, etc. But this is the idea. So, let me write it out. But I probably need some more space. So consider a canonical handwriting is getting from bad to worse. Data vector tree. And an economy under uncertainty. Remember, I did talk about expected utility, but expected utility is typically in a situation where you have risk so that you know what the probabilities are. But the point that I made is that in this framework of the more general data vector tree, what you have is preferences over commodity bundles. And those preferences can reflect your own beliefs. And therefore, it's more appropriate to think of this as uncertainty rather than just risk. Yeah? Yeah, you got it. Very often I will make comments of this sort which fill in gaps, which if you follow, that's fine. If you remember, it's all right. Even if you don't. So, you shouldn't worry about having jotted down everything because of the exam. That's not the issue. The exam is not a triviality, but that we take with it. It's based more on exercise. Let's start with an Arrow-Debreu equilibrium. X star 1, X star I, and P star. Now, there was a question that was asked at the end of the last lecture, which I perhaps mentioned here. So there was a question about the nature of the budget constraint in Arrow-Debreu. And I hope it's clear that the budget constraint is for each individual. We are not adding over agents in any way to get the budget constraint. And for each individual, given their endowments and given the prices for each of the date and state contingent commodities, you can specify the budget. So that's approved. So let that specification be an Arrow-Debreu equilibrium of the economy E. If the number of assets is equal to S and they are independent, which I'm not specifying here. Independent. Then there are, let's say you can specify portfolios theta I star star. The double star is to indicate that you're looking at a different equilibrium concept. Okay? portfolios and spot and asset market prices. So P star star 0, P star star 1, P star star S, and Q star star, such that, and now I need to use ME4 to do that, right here, such that the consumption bundles that you started with in the Arrow-Debreu equilibrium and the portfolios and the prices will spot as well as asset prices. Okay, all of that is an Arrow-Radnor equilibrium for the economic heat. Okay, and similarly, part 2 says, assume, so notice what part 1 says. Part 1 says you're starting with an Arrow-Radnor, with an Arrow-Debreu economy. Provided you have enough independent assets, you can construct an equilibrium of the Arrow-Radnor economy in which the consumption vector will be the same for each element. Okay, you have to construct portfolios and all prices, and you can do that. Part 2 says, assume J equals S, and I'm not going to write out the details of part 2, okay, but I will read it out and you have it in your notes. If there's a question, you can ask me. So again, you have as many assets as states and independent. The assets are independent, which I have not formally defined, but I've tried to explain. Okay. We'll write in the following way. Start with Arrow-Radnor equilibrium. There exist Arrow-Debreu prices such that the consumption vector for each of the agents in the Arrow-Radnor equilibrium is an equilibrium consumption vector in Arrow-Debreu markets, which you can write as Arrow-Debreu. So you get an exact equivalence between the two market structures. Yes. Now, I'm not going to prove it on the board. One of these two is actually a more difficult result to prove. The easier one is on the problem set for you to think about, and of course, as I've said at the beginning, the problem sets are an integral part of what I'm teaching. So you will see how to approach it and solve it once you've thought about it hopefully in the problem set. Again, there is no expectation that you're able to replicate that proof on an exam. That's not the idea. There will be some things where you will be required to do. We'll get to it. But not this. These sorts of things I don't want you to. It's pointless for you to sit and memorize these things. That's not the idea. You need to understand what is happening. What's the scope of things. So the key property is that you have competitive behavior, which we are assuming throughout, but more than that, It's the nature of the budget constraints. That's what it's saying. And that's what that example clarifies. Once you have multiple budget constraints, you need to be able to tie them in a certain manner so that markets work the way they would in Harold the Brook. And that certain manner takes this very simple form that you need as many assets as states of nature. You think of this as in linear algebra, in some form or the other, you've heard about when is it the case that the system of linear equations is a solution. Right? You need to think in terms of how many variables and how many equations. And this pesky condition called whether the equations are independent, which is a rank condition. Those of you who do econometrics will have been reminded of that. It's the same thing, actually. At the end of the day, that's basically what you're doing. Questions on anything that we've done so far? Any questions at all? So, for the exercise on the problem set, we will look at a special case, so-called arrow securities. Arrow securities are particularly simple. So again, let's think of the case where our first commodity is always bread. An arrow security says the following. The third arrow security, why do I start with the third? You'll see in a moment. Of course, talk about the first. The third arrow security pays nothing in the first state. It pays no bread in the second state. It pays 1 unit of bread in the third state and 0 everywhere else. Okay? So, the asset arrow security is 1 unit in state S and 0 otherwise. Going back to linear algebra, it basically works like a unit vector. Okay, in the same way as you can express any vector using unit vectors, that's basically the property that you need. And clearly, unit vectors have this property that you can't express one in terms of the other. They're all linearly independent. That's what independence is in the background. Okay? So the exercise has to be done with arrow security so that it's notationally easier. So we're talking about S arrow securities. Money, which we still haven't defined, is actually a particular case of an asset. But you will see very soon in tomorrow's lecture that it doesn't matter. Because everything that we've done so far describes an economy that has a final period. We've spoken about a finite number of goods. Nowhere have I said that you have more than that. Okay, and we will see very soon that in an economy in which money is rationally valued, if the economy comes to an end, money will never have any end. That will be the first thing that you do. Because that will tell us that you have to work with economies that go on forever, which is what makes this class difficult and interesting. But you needed to do the background work, some spade work, before you get there. There'll be much more spade work to be done. This needs to be done for sure. Okay? So, I have a couple of minutes, so I'm going to talk very briefly about where we go from here. So now in real world economies, of course, you have relatively few assets. You have relatively few assets, so there are lots of missing markets. In addition, enforcement of contracts is a problem. There are issues that have to do with the asymmetries of information, of course. But in general, enforcement of contracts is a problem, in particular for small amounts. Because you write a contract, who's going to go to court for that? It's costly fines. So for large contracts, of course, enforcement is captured through further details, which typically have to do with collateral. When you borrow to buy a house, where the bank's the effective owner, that's collateral. Not everybody gets it, that's a separate matter. But you get collateral. For smaller trades, we will see that the better way to deal with this is to use money. That's where money will come. Importantly, since it's money, and we'll see why, money will have value provided people believe that it will continue to have value. So expectations will start mattering. So you have to be very careful with these things. It's very easy to make loose statements. That's not going to get you very far. Okay? So we will be very precise in what we do. So expectations will matter. What will fiat money be? So this I'm not going to repeat tomorrow. For us, fiat money has the following properties. It's costless to produce. This is the first thing. The printing cost, which we ignore, is costless to produce because there was a time when it was primarily coins and things, but that was metal, and the gold content or the silver content in the metal became important. Fiat money doesn't have any of those issues. The metal content in these coins is negative, even though gold and silver prices have been exploded. No one's going and selling their coins. So it's costless to produce. It is durable. You can carry it from time across time. If at some point your notes become difficult to deal with, you can always go to a bank and exchange them for fresh ones at no cost. Or sometimes there's a marginal cost, very small. Okay. And fundamentally, you can know direct utility. There are models of money where agents get direct utility from them. These are called money in the utility function models. I don't teach them, although some of them are very famous, because I don't like them. I don't think that's a good way of doing it.